Talked about what it means for a function to be increasing. We said that mean value theorem can be used to prove that if a function is that a sufficient condition for a function to be increasing on an interval is that f prime be positive on that interval and it be continuous on that closed interval. Similarly, if it's continuous on a closed interval and f prime is negative on the interior of the interval, then it's decreasing on the closed interval. And if a function is continuous on the closed interval and f prime is equal to 0 for every value of x in the interior of that interval, then f is constant on that interval. We talked about critical numbers for a function. We look for critical numbers on an interval, basically in the interior of the interval, and they happen one of two places, where f prime is equal to 0 and where f prime is undefined. This is where a function may have a relative minimum or relative maximum. If it happens in the interior of an interval, then, well, let me get the theorem. If f is, sorry, we've not yet done the first derivative test. But we did example 1, is that correct? We did example 1 to indicate where it's increasing and where it is decreasing. Was just about to take us back over some paths we covered in section 4.2. Didn't want to do that. Let's pick up with the first derivative test here in section 4.3. All right. Suppose f is continuous at a critical point x sub 0. We've also called these critical numbers. Critical values also would work. And we have this additional information about the sign of the first derivative on intervals extending, open intervals extending both to the left and to the right. So imagine a point on the graph, and we know that to the left of this, I'm going to construct a little sine graph for f prime. Sine graph for f prime. On an open interval extending left from x sub 0, f prime is positive. So pluses right here. F prime is positive on that interval. And on an interval extending right from x sub 0, f prime is negative. So to the right, it's negative. Here is x sub 0, and that is a critical point, meaning that either f prime is undefined or f prime is equal to 0 right there. Maybe we have a horizontal tangent line. The pictures I may draw may imply that f prime is equal to 0, but it could be a point of non-differentiability. If f prime is positive, does that mean the function's increasing, decreasing, or what? Increasing. If f prime is positive, it's increasing, so the graph looking like that. It increases up to that point. On the other side of that, if f prime is negative, then it's decreasing away from that point. And so the conclusion is that f has a relative maximum at x sub 0. That seemed to make sense as far as the picture goes. Now, we'd like to be able to apply the first derivative test even if we don't have the picture in front of us. We just know that it's continuous at that critical point, and derivatives positive to the left, negative to the right, then we can see at this point at the top of a hill. Another sine graph, there's x sub 0. If f prime is negative to the left, but positive to the right, well, negative to the left would mean that it's decreasing coming into the point. F prime being positive to the right would mean that it's increasing going away from the point. So what's the conclusion? F has a relative minimum at x sub 0. So decreasing into it, negative derivative, increasing out of it, positive derivative. So it's a point at the bottom of a valley. And let's see, 2 pictures for the last one. Here's x sub 0. If f prime has the same sign, say f prime is positive on both sides. Positive, 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 positive. Well, let's see how such a thing could happen. Even if it's a horizontal tangent line, this could happen, say, for example, with y equals x cubed. Y equals x cubed, it's increasing, it's increasing, it's increasing, it's increasing, kind of levels off, and then continues to increase. So the slope of the tangent line goes to 0, but it never actually begins to decrease. And it's only at 0, only 0 at that one point. So if the picture's like this, and then that, it's increasing going to it, it's increasing coming out of it, there's no relative minimum, because look at any open interval, and I'm just going to draw this on the graph, but we think of it as being an open interval like that. There are going to be points above that value and below that value. Well, no minimum because they're points above, and no maximum because they're points below. So, neither. And suppose it's negative going in and negative going out, like this and like that. Not at the top of a hill, not at the bottom of a valley. So, neither a minimum or a maximum. So in a case like this, you might not know the function, you just have some information about the sign of the first derivative to the left or to the right, and you want to be able to conclude if it has a relative minimum, relative maximum, or neither. This is the first derivative test. And first modifies derivative, it's a test for relative extrema, which involves the first derivative. Section 4.4, we'll see a test for relative extrema, which involves the second derivative. Example 2. Analyze the relative extrema of this function. Well, I've got this piecewise function, which basically does everything we want it to do for the various scenarios. Let's see if we can differentiate it piecewise. So we have an idea of an expression which would define the derivative on the interval from negative infinity to 1, and an expression which would define the derivative on an interval from 1 to positive infinity. And because just by inspecting the graph, I think we'll be able to tell that there's a point of non-differentiability at x equals 1. So we're looking for zeros of the first derivative, and we're looking for places where the first derivative is undefined. So let's take this expression, d dx of x plus 4 times x plus 1, quantity squared. Let's differentiate it. And then at least on this portion of the graph, we will have an expression where if we substitute a number for x, it would give us the slope of the tangent line to the graph at any of those points. It won't be valid when x is greater than 1, but we can come up with a different expression for that one much more easily. So here goes. You think a product rule? That's one option. Or we could just multiply the whole thing out and use the power rule, but then we have to factor it back. I think we'll be able to salvage some of the factorability of this if we use the product rule. So it's going to be the first times the derivative of the second. So that becomes a 1, and then we multiply by the derivative of x plus 1 according to the chain rule, but that's 1, so it's not a big deal if you happen to forget to do it in this case. First times the derivative of the second plus the second times the derivative of the first. X plus 1 quantity squared times 1. Derivative of x plus 4 is 1. Now, kind of clean this up a little bit. This expression and this expression, two components of the entire derivative, each one of those has a factor of x plus 1. So my suggestion would be, as we're cleaning this up, rather than clearing parentheses, we take advantage of the fact that we see that common factor and we factor out the x plus 1. It'll just help us with the factoring on the back end here. So x plus 1, and then something like this. We look at the first component, this one right here, and we ask ourselves, What could we multiply x plus 1 by to get that? Two times that quantity x plus 4, that's what's missing. Then put a plus, and then ask ourselves, what could we multiply x plus 1 by to get this other component?
X plus 1.
X plus 1. That's bizarre. So I can make it go away just by scratching on it? Whoa! A whole new functionality of Microsoft Journal. So if I say something stupid and I want to make it go away,
it has to be a smaller scratch.
all right.
You'll probably turn the pen around though.
It was a nut. You think?
Yeah, that's how it usually works.
Yeah. That's why there's a big red eraser.
No, you have learned.
Wow. So if I say something stupid, like the fact that I've been using this for over a year now and not known that, I can just erase it. Wow. That's beautiful. All right.
There's still a dot of it
Yeah.
by the Cartesian plane.
A dot? Where? I'll get it.
By the Cartesian plane on the bottom right.
This dot? A dot here?
Yes.
Got it. Wow. Oops, another one. You learn something new every day. Yes, thank you. X plus 1 times 2x plus 8 plus x plus 1. X plus 1 times 3x plus 9. Now maybe factor out the 3. 3 times x plus 1 times x plus 3. So as I'm trying to differentiate this thing piecewise, f prime of x equals 3 times x plus 1 times x plus 3. And I can do this on the open interval, the one that does not include the 1. What happens at 1? It's not to say it's differentiable there, but it is differentiable everywhere less than 1. And over here, what's the derivative? ddx of negative 2x plus 22. Negative 2. So negative 2 if x is greater than 1. Now a couple things without pulling out the limit definition of derivative. Let me just establish some sufficient conditions for the function to be differentiable at 1. Basically, we need two things. As x approaches 1 from the left and as x approaches 1 from the right, the two pieces of the graph need to be, how to say this, f prime, the limit of f prime as x approaches 1 from the left needs to equal the limit of f prime as x approaches 1 from the right. They need to be able they need to be approaching the same amount of steepness, so that when they fit together, they'll have the same slope, like that. It also needs to be continuous there. Now the continuity is fine, because if you evaluate the top expression at 1, you get whatever 5 times 2 squared is. I guess that's 20. And if you evaluate the bottom expression at 1, then that's going to be 20. So they're both approaching the point 120. So it is going to be continuous, but from the left, the slope there is approaching whatever 3 times 2 times 4 is. Is that 24? I believe so. So the slope of the tangent line here, m sub tan equals 24, and that's dramatically different from the slope of the tangent line here, m sub tan equals negative 2. That there's an abrupt change, a discontinuous change in the slope of the tangent line from 24 to negative 2, so it results in a point of non-differentiability. It's not smooth. It's not smooth. So we can look for critical numbers now that we have the first derivative. We have critical number at 1 because it's a point of non-differentiability, and then we look for where f prime is equal to 0, where it's not going to be 0 for values greater than 1 because it's always equal to negative 2. But for values less than 1, it might be 0 if, so I'm trying to find where f prime of x equals 0. I would want to figure out where 3 times x plus 1 times x plus 3 is equal to 0. Yes?
Negative 1 and negative 3.
Yes. X equals negative 1 or x equals negative 3. They both qualify as critical numbers. So we have 3. Wait. No, it's okay. There's one more thing I need to say before I should have said they both qualify as critical numbers. I should have also said, and they're both less than 1. Because if one had happened at 2 or 3 or 4, it wouldn't have counted, because so we're only using this expression for x less than 1. But they're both less than 1, so it's good. The other one is 1 itself, because that's where f prime is undefined. F prime of x is undefined at x equals 1. So 3 critical numbers. What we want to do is apply the first derivative test at each of those critical numbers. All right, let's try it at x sub 0 equals negative 3. Now, one thing I want to do is a sine graph all the way from negative infinity to positive infinity. And if I have that complete sine graph, I'll be able to inspect the sine graph and tell what's going on with each of these critical numbers. It would seem a little bit unnecessary to do this one at a time. So let's construct a complete sine graph for f prime. I'll put those critical numbers on there in order from left to right: negative 3, negative 1, and positive 1, and choose a test number at each interval and evaluate the derivative at each interval. The derivative is only going to be able to change sign when either it's undefined or it's equal to 0. So it's not going to change sign within each of these intervals. So let's try negative 4, negative 2, 0, and 2 for our test numbers. F prime of negative 4. Well, I'll refer to the piecewise derivative that we have up here. If we substitute negative 4 for x, negative 4 plus 1 is negative 3. Negative 4 plus 3 is negative 1. So negative 3 times negative 1 is positive 3. Times 3 is 9. So it looks like 9. So the slope of the tangent line there at negative 4 is 9. It looks like it could pass for 9. The point is that it's positive. Positive slope. How about negative 2? Substitute negative 2 there and there. And we get negative 2 plus 1 there is negative 1. Negative 2 plus 3 is positive 1. So 3 times negative 1 times positive 1 is got to be negative 3. Negative 3, does this look like a slope of negative 3, perhaps? So since f prime of negative 2 equals negative 3, we get minuses all along there like that. How about f prime of 0? We still get to use this. 3 times 1 times 3, is that 9 again? Does it look like that line is parallel to that line? Maybe they both have a slope of 9, but it does look like f prime of 0 equals 9. So it's positive. And finally, f prime of 2. Now, if x is greater than 1, we're going to use this other expression, the negative 2. So f prime of 2 equals -2, and it is negative right there. Now we have the picture in front of us, but if we apply the first derivative test, kind of in the absence of this picture, we can say, okay, the first derivative is positive in an interval extending to the left, indicating it's increasing going into it, negative in an interval extending to the right of -3. So does it have a relative extremum there? It does. And the relative extremum, let's see. So analyze. So that's the conclusion. F has a relative maximum at x equals -3. That's one conclusion that we have, because it's positive to the left, F prime is, and F prime is negative to the right. How about at -1? It's negative to the left, yes.
Isn't that just a written version of visually checking to make sure it actually goes back down?
The pluses and minuses?
Mm-hmm.
Yes. The pluses and minuses, in the absence of the graph, if we have information about the function, but we don't have enough information to sketch a complete graph, then it's telling us this. So the minuses to the left of -1 tell us it's decreasing, going into the -1, and the pluses on the other side tell us it's increasing. So F, the first derivative test, has a relative minimum at x equals -1, and the pluses going into the 1 and the minuses going out, coupled with the fact that it is continuous there. It could get a little dicey if it's not actually continuous at that point, but it is. We've shown that. So F has a relative maximum at x equals +2. There we go. In each case, by the first derivative test. And the graph confirms it, of course. If y'all believe my graph.
Yeah, don't you mean 1?
I mean 1. And I meant, should have gone 1. I was referring back to this. This is where I initially, old habits are hard to break. F prime of 1. No. Yes.
It's undefined.
Is no. I was right the first time, but I was wrong the second time. F prime of 2 is negative, but I do mean at x equals 1, because 1 is the one we were testing it. Thanks. Yeah, that's right. Yeah, but 2 was my test number. So the test number was inside the interval. I evaluated it. It found a negative slope of -2 there. And so because it's positive going into x equals 1, it's negative coming out of x equals 1 has a relative maximum at x equals 1. Yeah. Sorry about that. Yes.
Weren't you taking your test numbers, in like the last one,
Mhm.
F prime of 2, you took the test number and you put it in the equation 3x plus 1, x plus 3? Is that right?
Actually, I put it right here. There was no place to put it because there's no... I just said because the 2 is greater than 1, then I look at this to tell me what f prime of 2 is. So it's just -2. And I got the -2 by taking the slope of this line.
So it doesn't matter what number we put up there.
So it would have been the same for 3 or 4 or 5. All throughout here, since the slope of this is -2, f prime is constant on that interval. But since it's negative rather than positive, we get a change in the first derivative test. Had it been 2x plus something, even if it had been continuous here and it looked like that, then what would have happened is that there would not have been a relative maximum there. If it had been positive going in and then still positive coming out of there, then we'd say it does not have a relative maximum at that point. That might have been a good example, but it didn't work out that way.
Is it safe to say by this point that 4.4 won't be on the test?
Yes, absolutely. 4.3 we'll finish in just a little while. And hopefully we'll start 4-4 today, but 4-4 will not be on this test, but the next one. Example 3. Okay, polynomial, and I've gone ahead and differentiated it, but it's not difficult, so maybe I should walk through it, because the derivative will not necessarily be provided on the test. So analyze the relative extrema. Well, we could look at the picture, of course, but the picture is there simply to substantiate what we're doing with the derivatives. Nice polynomial here. Analyze the relative extrema using the first derivative test. So this is going to be differentiable everywhere, so we won't get any critical points for points of non-differentiability, but there may be a couple points where the derivative is equal to 0, and we'll get critical points that way. So here goes, f prime of x equals 12, x cubed minus 84x squared plus 180x minus 108. We can factor out, I think, a 12. 12 times x cubed minus 7x squared plus 15x minus 9. Now, the third degree polynomial here was designed to have nice zeros. If the zeros aren't all that nice, we may have to content ourselves with decimal approximations for them. But since it is nice, when we appeal to the graph, we should be able to see what the x-intercepts are, so that a little bit of synthetic division will help us to find the other factors. So look at the graph. Really don't need the 12. I'm just concerned with the zeros of the x cubed. There's a 0 this one, it'll be a 0 if we tack on the 12. Minus 7x squared plus 15x minus 9. Zoom 6. By the factor theorem, zeros of this will point us to factors of the expression. And it would appear that 1 and 3 are x-intercepts. So just confirm that second calc value, x equals 1. Sure enough, 1 is a 0 of this expression, and 3 also is a 0. So we get a couple of factors, and I think I could even skip out on the synthetic division here, because again, looking at the graph, x minus 1 and x minus 3. But what can we say about the multiplicity of each of these zeros based on the graph of the polynomial? What do you think?
X minus 1 only has 1 because it crosses.
It crosses, so multiplicity 1.
X minus 3 has 2 because it touches.
It touches at x minus 3. So that has even multiplicity, and can't be more than a couple more for this function. The degree is only 3, so that one would have multiplicity 2. Now we could check and multiply this out and see, but it really doesn't have a lot of options other than this. This is pretty much the polynomial we're locked into. So this is f prime, and since this is f prime, we can set this equal to 0 and solve for x. By inspection, we can tell where the critical points, critical numbers, will be. So x equals 1 and x equals 3 are possible locations of relative extrema. They may or may not occur at these. We'll see it. We do get a relative extremum at one of these. We do not get a relative extremum at the other. To see where we get relative extrema, we get construct a sine graph for f prime. F prime can only change sign at critical numbers. So if we put a 1 there and a 3 there and test numbers in each of these intervals, whatever sign we get for the derivative in each of these intervals is the sign of the derivative throughout that interval. So what is f prime of 0? I think the best place to go is the original and just say I want to say it's negative 108, just from the original, because the 0 kills the first 3 terms and just leaves us with a negative 108. We could say 12 times negative 1 times the square of negative 9, but that's also negative 108. So negative 108, so the derivative is negative. And just by inspecting the graph, the function's decreasing throughout that interval from negative infinity to 1. Now what is f prime of 2? Well, here we probably should go here. 2 minus 1 is 1. 2 minus 3 is negative 1, but if we square the negative 1, we get 1. So 1 times 1 times 12 equals 12. And that's positive. Double check my arithmetic there, but hopefully when you substitute when you substitute 2 for x, you get 12. What if you substitute 4 for x? 4 minus 3 is 1. 1 squared is 1. 4 minus 3 is 1. 3 times 12?
36.
36. So that's positive. Whoa. You do a few of these, and you see plus minus, plus minus, plus minus. The sign tends to alternate, but then you run into one where it doesn't. We have pluses on both sides of this critical number, and when that happens, it's increasing into it, and it's increasing on the other side of it.
Like a tangent.
So well, there's the graph of kind of no vertical asymptotes here, but it kind of behaves that way, like tangent does, except that I guess tangent, I think has a slope of 1 maybe.
At some point.
At 0 rather than this where we're getting a horizontal tangent line. Yes.
Because the fact that 3 isn't a relative extreme will be because x minus 3 is squared, or is that just a coincidence?
We could probably find an exception to that rule, but it's something to look for. If we want to put it in the form of a conjecture, what could we say? There's no relative. If f is a polynomial and has a 0 of multiplicity, we need to have even multiplicity. It has a 0 of even multiplicity. Now f prime. F prime. So we're looking at f prime, and f prime has a 0 of even multiplicity. I guess we're referring back to this graph here and seeing where it just touched the x-axis there. Well, if that happens, it's necessarily, just since it just touches the x-axis there, it's not going to change sign. So yeah, you could say that. We'd have to really kind of fine-tune that, but I can see it's not a coincidence at all. That's going to happen every time you do this. Yeah.
Something to look for, I guess.
When that multiplicity is even, it'll just touch the graph, and so the first derivative is not changing sign. Then, according to the first derivative test, it's not going to have a relative extremum there. So f has no relative extremum at x equals 3. But f does have a relative extremum. What kind of extremum? Decreasing into it, increasing out of it. F does have a relative minimum, turns out to be an absolute minimum, at x equals 1. Here we go. This problem is maybe the trickiest one we'll have on a test all semester. Something like this. Because the problem asks you a question about the function f, but it doesn't give you a picture of the function f. It gives you a picture of f prime. So here's what I've got to do. I've got to capture this, paste that there, and capture this, and paste it there. And we want to answer a question about the function f, but we don't know what the function f looks like, what its graph looks like. This is the graph of f prime. So judging from the graph of f prime, we want to answer questions about f. Let's see what the questions are. A, identify the critical numbers of f. Now, if we do enough with critical numbers, and we're thinking about the graph of f, if we had the graph of f, we would think, oh, that's where it has points at the top of a hill, points at the bottom of a valley, maybe points of non-differentiability, although none of those here because it looks like a nice smooth polynomial. But how does that translate to the graph of f prime? What's going on with the graph of f prime if the graph of f has a point at the top of a hill or the bottom of a valley?
Isn't there such a thing as an antiderivative? Or is that what that is?
Well,
where you can sort of like have an inverse function.
There is, yeah.
Inverse derivative.
We're maybe thinking like that, and we'll do antiderivatives in the not too distant future, within the month.
Isn't there the fact that multiple different equations can come out with the same derivative?
Yeah, the antiderivative will not be unique. That's what we'll see. You can slide the thing up and down, and a lot of different functions will have this as their derivative. But I think we can still answer this question even in spite of the non-uniqueness of the antiderivative. There's some function f out there, a lot of them that have this as its derivative.
Just kind of work backwards with it, like seeing that x to the fourth is 1x to the fourth. So it's the same thing as x to the fifth would be the original function.
So x to the fifth.
But then you would take the 22.
X to the fifth. And then you would have like...
Well, what we'll see, once we answer this question, what we'll see is the antiderivative that I'm thinking of, one of many, is this. Okay, so no peeking, but 1/5 x to the fifth minus 22/3 x cubed minus 12x squared plus 45x plus any constant is going to work here for an antiderivative. But suppose we just have the picture. Suppose, and I guess I've spoiled it, suppose we don't even have this. Scratch it out. I can do that because I know I can erase it later. So, what's happening to the derivative when there are critical points? Critical points are points where the derivative equals what? 0, yes. So on the graph, where does it equal 0? Negative 3, 1, and 5. Okay?
Could you say that if y is going down as it crosses the x, then it would be a relative maximum, and then if it's going up as it crosses the point, it would be a relative minimum?
I think we can say that. Let's see why. If the graph, well, hang on. Wait. If it's pluses here, right? If it's a sine graph for f prime, I want to write pluses where the graph is above the x-axis, because this is f prime. Pluses where the graph that we see is above the x-axis, minuses where it's below the x-axis. So pluses, but more pluses, right? And then minuses, and then pluses. So this is our sine graph for f prime. Next question. Determine whether f has a relative maximum, relative minimum, or neither at each critical number. What's happening at negative 3?
Relative minimum.
Well,
it's not going to have anything.
If this were the graph of f, it would be relative minimum, but it's plus plus. So the graph of f is actually increasing going into this and increasing on the other side. So if we're trying to reconstruct the graph of f, We understand it's not unique. There are a lot of different f's that would work here. But something that's, got to be careful with maybe the curvature, do I? So maybe not. Increasing, and then horizontal tangent line, and then increasing on the other side of that. And what's happening? So neither. Neither. It does not have a relative minimum or a relative maximum. At 1, what's going on?
Positive to minimum, meaning it's going up and going back down.
Yeah. Plus to minus. So going up into it, down, out. So relative maximum. And at x equals 5. Going into it, it's decreasing. Coming out of it, it's increasing. So relative minimum. Let me continue with the graph. So I have to be careful because there's something special that happens involving the second derivative. So something like, where's that relative maximum going to occur? At 1?
Maybe drawn a little higher.
Like that, maybe? Maxes out at 1, and then comes back down, and then a minimum at 5, and then increasing the rest of the way. So something sort of like this. It's freehand, so could be off in proportions and various things like that. But to reconstruct the original function, these are some considerations. If we had some additional considerations involving the second derivative and concavity and inflection points and things like that we'll see in 4.4, then we can be a little bit more precise with it. But that's the idea. And what is the C part? Oh, do your best to sketch a rough graph of the function. Okay, we did that. So there it is. Now, the actual one looks like that. So it kind of, compared to what we have, yeah, I think that's fairly decent. Maybe I should have leveled it off a little bit more at -3. I'm not real thrilled about what I did there. Horizontal tangent line right there, so level and then up. But otherwise, seemed like it was okay.
Would it help if we marked where we were having maximums, minimums, or just flatness?
I think so. Yeah, I think if you just maybe draw something like that, and something like that, and something like that, and then indicate, oh, that's got to be the bottom of a valley, that's got to be the top of a hill, that's got to be neither one, and then fill in the rest of the graph based on that. That would be very helpful, I think. And this was what used to be a WebAssign problem. Yeah. That evidently students were struggling with, so I put in the notes. Let's look at 4.3 exercises and see what would be some good ones, some additional ones to practice on in your preparation for the test. Section 4.3. Then we'll see if we can say a little bit about 4.4 before we go today. Is this 4? What is this? It's 4.3. Not so much delta intervals where it's increasing or decreasing. If it provides the picture. Okay. Beginning with problem 9. .39 11 15 should be fine because when you take the derivative of that, you lose the x. So you might have the trig function and a constant, but you don't have a mixture of a trig function and a non-constant polynomial. I wonder if 17 is going to be as ugly as the corresponding one in the previous section. I almost think 18 might be nicer than 17. And I think 16. Good grief. Help me out a little bit. Why don't I like the even numbers? I like 14. That is not useful. Okay, the 13 and 15. Find the critical numbers. Find the open intervals on which the function is increasing, decreasing. Locate all relative extrema. So 25 looks good. 27 for sure. (31 and 35), they're not polynomials, but that's probably a good thing. Get points of non-differentiability and possible location of relative extrema at those critical points. 37 is a nice one. We did a piecewise function, but I don't think 43 would be out of bounds. Is there anything? Ooh, 47. 47's nice. 47, I like that. And then they get more extreme. Apply the first derivative test to identify all relative extrema. Use a graphing utility to confirm your results. 59. So we really do have time to work all these problems between now and Wednesday morning, right? Well, we have time to glance at them and say, yeah, I can sort of do that. We'll see.
I have a question though.
61 to 65, yes.
On the
Question.
next test, are you going to go back to having homeworks, or are we?
I think to some extent I will, and on the last couple tests, maybe we're down to the last couple of tests at this point. The last one for sure, maybe the next one next to the last one. I've already got some problems worked out, so it should go back. This is just when I originally did this, it was not something that I could type up very well. It was a lot of handwritten work, and at the time I didn't have a tablet PC, and it was real arduous to do it. Paper, scan, yeah. It would work, but then when I want to edit it, it becomes a nightmare.
Have to draw up a mess.
I still say you give us till Monday.
85. Use the graph of f prime to identify critical numbers. That's just like the problem we finished. 85 is a fantastic one and virtually guaranteed to have something like that on the test. 85. Conceptual stuff there is good. Ooh. That should be plenty. I'm going to say more about this motion along a line in the section entitled A Summary of Curve Sketching. That's going to be my principal examples that I'll use in a summary of curve sketching. So I'll come back and pick up some of those 4.4 examples and make up some 4.3 examples toward the end of the section and make up some of my own when we get there. So you have kind of an idea what to study for the tests.
What question should we do for 3.7?
3.7. Those ones that I listed in the homework actually for last time. If you go there and click on the exam 3 homework, just pick up with with those. It was the related rates problems, relationship between the volume, height, radius, length of a cylinder, and formulas. Formulas, I may very well...
By the way, why are they hyperlinked?
They're hyperlinked to YouTube videos.
Oh.
Have y'all looked at any of the YouTube videos? Yeah, if you click on it. Yeah, these guys are really good. I forget exactly where they are. This Bull Clio 1, but they have a lot of these in there. It's not a thrill a minute, but it is. They are really clear. They speak slowly, and they support everything they say with graphs. They do a really good job, and a lot of these are linked to those. Some of the first ones, like up here, are linked to Khan Academy. Mr. Khan does a pretty good job most of the time. I think maybe this one was a pretty good one. If you want, I suppose you could just go to the end and look and see what's been written there. But he'll talk you through it. So that's something to consider. Maybe not as nice as having them in printed format, but they'll give you step-by-step instructions. They do a pretty good job. Set it equal to 0. Let's find the critical points. So 3/4 x squared equals 3. X squared equals whatever 4/3 times 3 is. So x squared equals 4. So x equals plus or minus 2. So a couple of relative extrema here. So 2 and negative 2 are values where the first derivative is equal to 0. So let's construct a sine graph for the first derivative, sine graph for f prime, and choose some test numbers that are inside of these intervals. And this particular first derivative should be pretty easy to evaluate. If we square negative 3, or positive 3 for that matter, we get 9. So in either case, 3/4 of 9 is 27/4, and 27/4 minus 12/4, 3 equals 12/4, is a positive number of fourths, 15/4. So the first derivative is positive here, and the first derivative is positive here as well. Get the same value for negative 3 and positive 3 because we just begin by squaring it. They have the same square. If we evaluate the first derivative at 0, f prime of 0 equals negative 3, and that's negative. What do we say, 15/4 for that one? 15/4 for that one. So according to the first derivative test, the pluses indicate it's increasing going into it. The minuses indicate it's decreasing going out of it. So it looks like a relative maximum at negative 2. At positive 2, the minuses indicate that it's decreasing going into it. The pluses indicate that it's increasing going out of it. So relative minimum at positive 2. So it has a relative maximum at each one, and let me refer back and just see exactly how I define relative extremum to see the to see the role of the y coordinate there. Nope, that would have been back 4.0. 5.1. When we talked about a minimum or maximum, didn't put the word relative in front of it, basically that meant absolute maximum in the interval, absolute minimum in the interval. And it was important to consider the function value, that maximum value or the minimum value, to evaluate the function there. For the existence of a relative minimum, or to say it has a relative minimum or relative maximum, it's not going to be as crucial for you to tell me the value of that relative maximum or the value of the relative minimum. We haven't been doing that in any of these examples, and so I'm not going to do it here or ask you to do it on the test, simply to say it has one there, and not to take the time to substitute the -2 for x in the original function, or the +2 for x in the original function. We do that when looking for an absolute maximum or an absolute minimum, not as crucial for a relative maximum or relative minimum.
So maybe the 5 minutes sort of just write it out.
What's that?
Instead of 5 minutes sort of just write it out, but there's the maximum minimum.
Yes, so f has a relative maximum at x equals -2, f has a relative minimum at x equals +2. Okay.